In this lecture, let's understand about linker scripts. First of all, let's learn what exactly is a linker script. Linker script is a text file which explains how different sections of the object files should be merged to create an output file. Linker and locator combination assigns unique absolute addresses to different sections of the output file by referring to the address information mentioned in the linker script. Linker script also includes the code and data memory, address, and size information. So inside the linker script, you have to mention the various memories which are present on your target board, and also you have to mention the size and address information. Linker scripts are written using a new linker command language, and GNU linker script has the file extension of .ld. You must supply linker script at the linking phase to the linker using -t option. We'll see that when we run the command. To write a linker script, you have to first understand different commands used to explain various things in the linker script. There are commands like entry, memory, sections, keep, align, and et. There are many commands, but I have just listed here some of the important commands. First, let's explore about the entry command. This command you have to use to set the entry point address information in the header of final ELF file generated. What this command does is it just populates entry point address information in the ELF file header. That's it. In our case, reset handler is the entry point into the application because that is the first piece of code that executes right after the processor reset, isn't it? The debugger uses this information to locate the first function to execute. This is actually not a mandatory command to use, but this is required when you debug the ELF file using the debugger such as GDB. This is given just for the debugger's sake. Strictly speaking, it is not required. This is how you should use the entry command. Entry, and in the parenthesis, you have to give the symbol name. That is the function name, which is an entry point into your application. In our case, we are going to write something like this, entry reset handler, where reset handler is a function name, or you can also call it a symbol. Let's use the entry command, and let me get back to this memory command. Let's head over to my workspace and let's create one linker script here. You have to give the file extension .ld. First, let me open my command prompt here. I'm going to create one linker script. Let me call it as stm32ls linker script, and I'm going to give the extension .ld. Here it is. Let me open this file. First, let's use the entry command. You can use the entry command, so make sure that all are capital letters. After that, open the parenthesis, and here you have to give the symbol name. Symbol name is, you have to refer to your startup code here. This is our entry point. Let's copy this function name and paste here. That's it. There is no semicolon here. You should not give any semicolon. This will set the entry point address in the final ELF, which we are going to generate next. Let's explore about the memory command. This command allows you to describe the different memories present in the target and their start address and size information. The linker uses information mentioned in this command to assign addresses to merged sections. That is what we call as relocation. Sections must be relocated to different addresses. That is done by the address what you mention in the linker script by using the memory command. The information is given under this command also helps the linker to calculate the code and data memory consumed so far by the application and throw an error message if data, code, heap or stack areas cannot fit into available size. By using memory command, you can fine-tune various memories available in your target and allow different sections to occupy different memory areas. Typically, one linker script has one memory command. So you will generally find only one memory command inside a linker script. Let's see the syntax of memory command. You have to use the name memory here. That's the command name, which must be in capital letters. Then you have to give the body of that command. And inside the body, you can write many statements in this format. The memory statement has three parts. This is a label. This is a origin, comma, length. A label will have its own attribute list. Attribute, if used, it is optional actually, but if used, you have to give that in the parenthesis. Label, colon, origin, and comma, length. Let's understand what exactly is a label. Label defines name of the memory region. It is just a label or a user-defined name given to a particular memory region. This name will be later referenced by other parts of the linker script. By using this statement, you just give a name for a memory region which is present in your target. And after that, using this origin name, this is a standard keyword of the linker. You have to use exactly like this. Using this name, you have to mention the origin address or the start address of that memory region. That's why this defines origin address of the memory region. After that, you have to mention the length information. Defines the length information of the memory region. Again, you have to use the standard name length here. Length is equal to, you have to mention the size here. Don't worry, when we see the example, it will get cleared. Memory command may have multiple such statements. Let's move forward. Let's talk about this attribute. This defines the attribute list of the memory region. Valid attribute list must be made up of these characters which are mentioned in this table. If you mention R here, then that means read-only section. W means read and write sections. X means sections containing executable code, like that. You can mention these attributes either in capital letters or in small letters. And you can also combine two or more attribute letters. So we'll see that when we do an exercise. Let's move forward. Let's take an example of our microcontroller STM32F4VGT6, which has 1 MB of flash size, and it has SRAM1 of 112 kilobytes and SRAM2 of 16 kilobytes. Let's see how we can write a memory command for this. Let's type the command memory and then give the body by using these curly brackets. After that, let's define available memory regions of our target. In our target, three memory regions are available: flash, SRAM1 and SRAM2. First, let's explain the first memory region. First, give the label for the memory region. Let me call it as code memory, or you can also call it as ROM, or you can also call it as flash. So any name you wish you can give. I'll just use flash. And the attribute list you have to give in the parentheses. I would give readable and executable, because flash memory contains code, isn't it? That is not writable by the user program. That's why I would omit W here. I would just use read and executable. Colon. Let's write the origin. For that, you have to use the standard name. Origin is equal to, what is the origin of flash? 0 cross 08 00 0000, comma, length is equal to 1024 kilobytes. For the kilobytes, you can write K. That will be expanded to number of kilobytes. Or you have to mention after multiplying with 1024 here. Otherwise, just mention K here. So that is the correct syntax, no problem. And after that, let's explain the SRAM1. SRAM1 you can read, write, execute. You can even execute code from SRAM. Origin is equal to 0 cross 2 0 0 0 0 0 0 0 and length is equal to 160K. SRAM2, again attribute I can use RWX. Origin is equal to, here you can use, so what is the origin of SRAM2? The end of SRAM1 is nothing but origin of SRAM2. And you can calculate something like this. You can copy this here plus this much 116K minus 4 you have to do. This is the origin. Or you can calculate the final value and you can write it. After that, length is equal to 16K. If you have more memories in your microcontroller, then you can mention them only if you have any plan to use them in the linker script. Otherwise, need not to mention. For example, backup SRAM. So this microcontroller also has backup SRAM that you can explain here. And if your microcontroller has CCM memory, and if you have any plan to use that by using the linker script, then you can explain the CCM memory and various other things. For our example, we only want to use SRAM and the flash. That's why I would just club this SRAM1 and SRAM2 to just make it as SRAM. I would not need these two segregations here. Since in this example we are just using flash as our ROM and SRAM as our read-write memory, I would just use two statements here. I would just consider SRAM 1 and 2 as whole SRAM. That's why I would just write SRAM here and I would just write it 128K. This is our memory command which explains two memory regions. One is code memory, that is this one, and another one is data memory, which is SRAM. So let's explore about sections command. Sections command is used to create different output sections in the final ELF generated. This is an important command by which you can instruct the linker how to merge the input sections to yield an output section. This command also controls the order in which different output sections appear in the final ELF file generated. By using this command, you also mention the placement of a section in a memory region. For example, you can instruct the linker to place the .text section in the flash memory region, which is described by the memory command. Let's see one example of sections command, how to use this command. So it all starts with the command keyword sections. This is a standard keywords. You have to write in all capital letters. And after that, this is a body. Sections command is used to create different number of output sections in the output file. For example, in this case, the output file generated will contain two sections. One is .text section and another one is .data section. This command instructs the linker to create two sections in the final output file generated. In this case, the output file is nothing but .elf file. The sections will appear exactly in this order. First, .text section will appear, followed by .data section. Let's take this example. This is one of the output section which we want to create. Here, this is a label of the output section. This label can be anything. It depends on you. You can give any name you want, but you have to follow some standard naming convention. This is the output section name. This is the body, and this gives the address information to the linker and the locator where to place this section in the memory. This is a combination of VMA and LMA. where LMA stands for load memory address and VMA stands for virtual memory address. And more on that we'll see later, how to use this syntax properly. But this actually gives the section placement information in the memory. This output section is used to merge all other sections of individual input files. How many input files we have got in our project? So we have got 3 input files, isn't it? Main.o, led.o, and we have one more, startup.o, as I described in the earlier slides. And each object file contains its own different sections like text, data, BSS, constant. By using this output section, we are going to merge all sections of input files like this. Let's use this text section to merge all ISR vector section of all input files. Merge all .text section of all input files and merge all .ro data section of all input files. After that, just mention the address here where those sections should go. And after that, let's use another output section .data to merge all data section of all input files. Let's edit our linker script to create some output sections. I'm going to write sections here and I'm going to open the brackets. The first output section, what I want to see in the output ELF generated is, let's say, .text. This is the name of the output section or label. You have to give colon and its body. Here, let's merge text section of main.o, led.o and startup.o. How do you write this? You can use one shorthand notation. So you can mention something like this. You can use .text of all input files. You can use the wildcard character here, star, asterisk you can use. This denotes consider .text of all input files. Instead of writing .text of main.o, ld.o, startup.o, you can use this shorthand notation. If you again refer to this diagram, this explains storage of final executable in code memory. The initial code space must contain the vector table. After that only the .text section should appear. We have to follow this order. Otherwise our application will not work properly. That's why what you have to do is you have to first merge the .isr underscore vector section. .isr underscore vector of all input files. You can use wildcard character. For this application, it is not required because there is only one ISR vector section. But that's okay. This is a generic statement. After that, according to our diagram, we want to place .ro data. Let's do that. Star of .ro data. This output section comprises of all these individual files section. We just created one output section, that is .text. Now you have to decide where you wish to store this section in the memory. That means you have to mention 2 memory regions for this section. One is VMA and another one is LMA, where VMA stands for virtual memory address and LMA stands for load memory address. Before that, you have to ask one question. So do you relocate this section in your startup code? No, we don't relocate this. This is going to be stored in the ROM space. ROM in our case is flash. It doesn't have any relocatable address. That means VMA and LMA are same for this section. That is flash. This section should go to flash. And flash begins from here. That's why next step is you have to mention the section placement by using the symbol greater than. What you do is give a greater than symbol, and here you have to mention the VMA. Then use the command at greater than symbol, give space, and now mention the LMA. VMA in this case is flash and LMA is also flash. Once the linker sees this, what it does is it generates absolute addresses for this section, and that addresses fall in the memory region what you mentioned in the VMA. After that, the linker also generates load addresses for this section. That addresses fall in this memory region what you mentioned after the at command. Don't worry, so again when we disassemble the final executable by using disassembly tool, you can understand more. In this case, both VMA and LMA are same. You need not to write something like this. You can just omit this, so you can just mention like this. This means that VMA and LMA are same. Let's create the next section, dot data. And again, I'm going to merge data sections of all the input files here. The dot data section is relocatable, isn't it? This must be stored in flash, but the startup code has to copy this section from flash to SRAM. That's why the load address is fixed, that is flash. In the flash, first this section will appear, and right after that, this section will appear. That's why you have to mention load address as flash. What about the VMA? And the VMA in this case is SRAM. When linker sees this, so it will generate load address for this section, which falls in flash right after this section. But the absolute address of this section will fall in the memory region SRAM, which starts from this memory location. I will show you practically, so when we disassemble the code. That's it. We created two sections. This is for initialized data. What about uninitialized data? That we call as BSS. Let's create one more section, BSS. And again, this is nothing but collection of all individual BSS sections of different input files. And as I said, this will not get stored in the flash. That's why it has only VMA. So it doesn't have any LMA. VMA is nothing but SRAM. We just created a linker script which can generate 3 output sections for the final executable. And we have to keep improving this linker script. This is not final. In the next lecture, we will explore one more important concept of the linker script, that is location counter. Now we created our linker script according to this memory layout. And the data section which is stored in the flash needs to be relocated by the startup code. But to relocate this section, you need a couple of information. At least you should know the boundary where RO data ends, where this section ends. So you should know this information. And after that, you should also know the size. Or if you know the beginning address, or if you know the ending address of RO data section, and if you know the ending address of dot data, then you can calculate the size. You can use this information in the C startup code to relocate the section. Otherwise, you can't do it, isn't it? Now, the question is, how do you trace such boundary information in your C program? The answer to that question is the boundaries can be tracked inside the linker script. And after that, that boundary information can be passed to the C program. For that, the linker gives you one nice feature called location counter. This is a special linker symbol denoted by a dot. Location counter is denoted by a dot. This symbol is called location counter because linker automatically updates this symbol with location information. So you can use this symbol inside the linker script to track and define boundaries of various sections. You can also set location counter to any specific value while writing linker script. Location counter should appear only inside the sections command. You have to remember that. So you cannot use that outside the sections command. That would throw you linker error. The location counter is incremented by the size of the output section. That helps you to track the boundary. Let's make use of location counter in our linker script. Before that, we have to explore one more thing, that is linker script symbols. Creating linker script symbols. We use location counter symbol with other linker script symbols. Let's explore about the linker script symbol in the next lecture. In this lecture, let's understand about linker script symbol, and later we can understand how to use the location counter and linker script symbols together. What exactly is a symbol? A symbol is the name of an address or memory location. A symbol declaration is not equivalent to a variable declaration, what you do in your C application. For example, consider a C program, let's say main.c, and let's say you have this statement. What is this? This is a variable definition. Here, your goal is to store a value 100 into some memory location. Basically, this is a global variable. If it is a global variable, then it will go into the data memory, but you don't know the location. If you want to modify the value of this variable, then you just do this. Here, you don't know the location where you are going to keep this value 50. You just write by using the variable name. But at the background, it must be converted into an address manipulation. At the end of the day, everything is address. So the value 50 must go to some address, isn't it? In this case, some memory location must be modified to put the value 50. The question is how this variable name is replaced by the address. That happens because of the symbol table. When you compile this program main.c, you know that it will get converted into main.o. And in the main.o, the compiler maintains a table called symbol table. For the compiler, this is not a variable name. It's a variable name for you, for the programmer. For the compiler or linker terminology, we call it as a symbol name. It's a symbol name. A symbol is a name given for an address. The symbol table majorly maintains two columns. One is address and another one is symbol name. Here you can see that there are two symbols. One is this one, that's a variable name, my value, and it has its corresponding address. When you do this, that means here you are trying to modify an address. For you, you are trying to modify a variable, but at the background you are trying to modify an address. So the address will be resolved by looking into the symbol table, which is maintained by the compiler in the object file. If you consider this function definition, here this is a function name, fun1. Basically, the function definition belongs to the text section. It is stored in the code memory. This is also maintained in the symbol table. Here, this is a symbol name. Fun1 is a symbol name, and this is the associated address of that function in the code memory. Like that, every object file maintains the symbols and its associated addresses. Please remember that in your C program, you don't write symbols. What you do variable definition, you do variable declaration, you do function definition. So you don't create any symbols in the C program. Symbols are created and maintained by the compiler. That's why we never worry about creating symbols in the C program. Now the scenario is different. We have to worry about creating some symbols because we are writing the linker script. And inside the linker script, we want to catch these boundary information. How do you store the boundary information? So would you create variables? No, you can't, because we are not writing any .c file which is going to be compiled by the C compiler, isn't it? We are writing linker script, which is just a text file which is going to be passed by the linker. That's why we cannot create any variables to catch or store the boundary information and other things. That's why we have to create some symbols. That's what we call as linker script symbols. Take a look into this example. So here I have created a couple of symbols. Symbols is written exactly the same way how you write variable definition. For example, consider this. Please note that this is symbol definition or symbol declaration. This is not a variable. What is symbol? A symbol is a name given for an address. This is the value of the symbol. When linker sees this, because compiler will not see this. Why? Because it is in the linker script. Linker script will be passed to the build system during linking stage, isn't it? So linker is going to see this. When linker sees this entry, it is going to add this entry to the symbol table of the final executable. That's it. Symbol name and its associated value, like this. This is also one more symbol declaration. Here you can see that I have created one more symbol to catch the end of text section. Here the symbol name is end of text, and that is equal to the dot operator, that is the location counter. Remember what I said in the location counter explanation? Let me open that. The location counter is incremented by the size of the output section. This will happen automatically by the linker. At the beginning, location counter is equal to the VMA. That is assumed by the linker. That means dot is equal to initially this address 0x08000000. Here location counter value will be incremented by the size of the text section. That's why this symbol will now hold the end of text section, the address of end of text section. You get the boundary. Now you can export this symbol to the C program and you can access the exact address where the text section ends. So we'll see that later. Similarly, you can create any number of linker script symbols and you can store some value here and you can access that from the C program. We will create some linker script symbols to catch the boundaries of different sections. With that note, I would like to end this lecture, and in the next lecture, let's edit our linker script to create some symbols. In this lecture, let's edit our linker script to create some symbols. Let's refer to this diagram to catch some boundary addresses. First of all, in this diagram, so this is a place where the text section ends. This is the beginning of data section in the ROM. We should know this address. If we know this address, then from this address we can start copying from flash to SRAM. And we should also know the start address in the data memory. This is a source address and this is a destination address. We should know both source and destination addresses. After that, we should know the size of this data section, that is how many bytes of data we want to copy from code memory to data memory. We at least need all these three information. Let's create some symbols to store these values. Let's get into the linker script and let's create one symbol. You have to select some meaningful symbol name. Now the rules what you follow to write a meaningful and legal variable name, the same rules you can follow to write a symbol name. Let me create one symbol name underscore e text, that is end of text. And I equate this to the location counter, the dot operator. Remember that this symbol declaration must be terminated with a semicolon. What did I do here? I stored the value of location counter into a symbol name underscore e text. As I said in the previous video, this location counter symbol will contain the updated address information of this text section. This is end of text, isn't it? And after that, so here let me create some more symbols. That is s data, start of data is equal to the location counter. You have to remember this. Location counter always tracks VMA, not LMA. Location counter always tracks VMA. That's why at this point, the location counter value is nothing but start of VMA, which is nothing but SRAM address. That is nothing but this one. Let me create one more linker script symbol. End data is equal to location counter. Here, the location counter value will be updated by this much size. This is e text. This is s data. This is e data. If I do e data minus s data, I would get the size. This is a source. This is a destination. I can derive all other information. Let's create some linker script symbols for BSS section. So I would call this as underscore start BSS is equal to the location counter, and here I can create one more symbol, EBSS is equal to location counter. We almost finished writing our linker script, and in the next lecture, let's use this linker script to link our project to create final executable. Complete up to here, and we'll explore about linking in the next lecture.